Hello good people and welcome back. In this video what we're going to do is wrap up the discussion in unit 11 when we're talking about binomial trees. In the first video what we did of this unit, what we did was talk about risk neutral probabilities or risk neutral valuation, and we also talked about no arbitrage approach to valuing put and call options. And in this video, in the last video we used a one step, which means that we only stopped at that one period. In this video, we're going to move that forward to looking at a multiple steps. So we're going to essentially look at the two steps, and the process is the same. The idea here is going to be that we have a stock price today that can increase over the next, say, 3 months, and it can increase to stock up or it can decrease to stock down. And over the following 3 months, the stock can decrease even further. Actually, I'm going to use that. It can decrease even further to what we're going to call stock down. That's if it's decreased twice, or it can increase some, which is what we're going to call stock down, because it was decreasing and then it increased. So stock down and up. Now, at this point, it could also decrease or it could increase, in which case we can call stock up. And we say, well, if we, in the time period here, between these two periods here is also 3 months. And so the question is, if you have a call option here, how do you value it? Well, when we looked at the one step, which was just this, what we did is we said the call option was equal to the probability that the stock price was increasing multiplied by call up, plus the probability that the stock price is decreasing, which is 1 minus P, multiplied by call down, and then we took the present value of that. This was our risk neutral approach to valuing a call option. So the process is going to be very similar. It's going to be fairly simple. What we're going to do is going to do that twice, essentially. We're going to do that for the first window. We're going to value the option here. So that's going to be call up, and here we're going to have call up, and here we have call up, down, and here we have the call value, and here we have call down, and we're going to have call down. So essentially, we're going to say call up here is going to be the same, and we're going to call this, say, probability 1, and we're going to say probability 2, and here we're going to say probability 2 again, and that's going to be it. So we can put it that way, and we can work with that. So our call up is essentially going to be equal to the value of the call option over that period. So it's going to be equal to P2, which is the probability that stock price increases. Call up, we're here, right? We're not here yet. We are here still. It's going to be equal to P2 multiplied by call up plus 1 minus P2 multiplied by call up down, and then we do present value. That would be call up, and then call down would be equal to, this is our call down, the same process is going to be equal to P2 multiplied by call up down plus 1 minus P2 multiplied by call down, and then present value. Once we have call up and call down, we can just come in and plug them in here using P1 this time and P1 here, which is that value, and we'll have our call option price. So let's work with an example. I know this looks crazy, but let's work with an example, and that's going to make a whole lot more sense. Alright, so this is what we have. We have a stock price today that's valued at $20. It can increase to 22, that's what we had, or it can decrease to 18. That's for the first phase. Over the second phase, it can increase further to 24.2, or it can decrease to 19, or it can decrease to 19.8, which means that this can increase to 19.8, or it can decrease further to 16.2. And the question that we have is, if you were to value a call option on this stock with a strike price of 21, and this has a maturity of 3 months here, and another maturity of 3 months here, what would that call option value be equal to? Now, if the stock price increases from S0 to 22, what we need to find is what is the call option value here, what is the call option value here. But we know that the call option value is the present value of the outcome, so it's going to be call up plus 1 minus P call up down, and then we do present value, right? That's what we looked at earlier. And so what is the value of the call at this point? If the stock price is at 24.22, the payoff is going to be stock up minus strike, which is going to be equal to 24.2, I should say. 24.2 minus 21. So our payoff here is essentially going to be equal to, that's going to be 3.2. I think that's what we have, right? 3.2. So our payoff here is going to be equal to 3.2, and the 3.2 really is just the stock up, which is this value here, minus the strike price, which is 21. So that's our call up, which is going to go there. What is the call up down at this point? Well, at that point, what we're going to have is the maximum again of stock up down minus K, and stock up down is 19.8, so we're going to do 19.8 minus 21. So that's going to give us a negative value, and remember we take the maximum of 0 or the value here, so that this is going to be equal to 0. So our call up down here is going to be equal to 0. Now if we find the present value of that, what do we have? Well, we're not there yet, right? Because we need to find these probabilities. And remember, we call the probability here P2. And so we're going to do P2 here, which means that we're going to call this call up. So what is call up? Which is the value of the option at this point. The value of the option at that point is simply going to be equal to P2 multiplied by call up, which is 3.2, plus 1 minus P2, which is essentially the probability that the stock price decreases, multiplied by 0. So that's simply going to be equal to 0 there. And then we take the present value of that. So in this case, what do we have? What is P2? P2 is going to be equal to the exponential of RT minus D divided by U minus D. Now, what is U? U is equal to S up divided by S0. In this case, if we are only looking over this period here, S up is going to be 24.2, S0 is going to be 22. So what we're going to have is 24.2 divided by 22, and that's going to be 1.1. So it's going to be 1.1. And D is simply going to be equal to S down divided by S0. and S down is going to be 19.8. So it's going to be 19.8 divided by 22. And so we're going to do 19.8 divided by 22. We're going to have 0.9. Now let's verify this. Let's do 1 over u, which is equal to 1 over 1.1. That's equal to 1 divided by 1.1, 0.9. 0.9. So that should be equal to D. So we verify that expression that we had there. Remember, u is equal to 1 over d, and d is equal to 1 over u. So we have u and we have d for this first phase, which means that P2 should be equal to exponential of 12% multiplied by 1/4, because that's 3 months, minus d, which is 0.9, divided by u minus d, 1.1 minus 0.9. So P2 is going to be equal to 0.12 divided by 4 second function exponential minus d 0.9 equal, we're going to divide that by open parenthesis 1.1 minus 0.9 close parenthesis equal. That gives us a probability of 0.6522, the same that we had earlier. So this is going to be equal to 0.6522. So we know that P2 is going to be equal to 0.6522, which means that 1 minus P2 is going to be equal to minus plus 1, 0.3477, 0.3477. And so with this, we can find call up, which is the value of the call here, and we also need the value of the call down. And the value of the call there is going to be equal to, all we are doing is applying the risk neutral probability approach. And so once we did that, what we're going to have is essentially the following. Call up is going to be equal to, you remember that, P2 call up plus 1 minus P2 call up down, and then present value. You remember also that call up down is equal to 0, so this goes away. Really what we have is call up is equal to P2 call up present value. So that's going to be equal to P2 is 0.6522, which is our probability. Call up we found that to be equal to 3.2. So we're going to multiply this by 3.2, and then we then take the present value of that, that's exponential of minus 12% divided by 4. That's our present value factor. So what we're going to have is essentially the following. 0.12 minus divided by 4 equal second function exponential, and then we're going to multiply that by 3.2, and then we're going to multiply that also by 0.6522, and that's going to give us a 2.2025, which is going to be call up. So if we go back up here, our call up is going to be 2.20, what was that? 2.025. So it's going to be 2.025. That's going to be call up. Now we need to find call down. And we're going to apply the same thing, right? Call down is going to be equal to P2, but this time we're going to say call up, call down up, right? And then call down down. So what we're going to have is call down up plus 1 minus P2, call down down, and then we're going to take the present value of that. P2 is the same. Let's verify that. What is U here? U there is going to be equal to 19.8 divided by 18. And so 19.8 divided by 18 is going to be equal to 1.1. That's equal to U. And we know that D is equal to 1 over U, so that's also going to be equal to 0.9. So that means that P2 here is exactly equal to what we had earlier, which is exactly equal to the 0.622 that we had there. And so P2 is going to be 0.6522. Call down up. What is the call down up? We found that the call down up here for us was equal to 0, which means that call down down is going to be equal to what? It's going to be equal to stock down down minus strike, and that's going to be equal to 16.2 minus 21. So that's going to be negative, which means this is also going to be equal to 0. So call down up is going to be 0, and call down down is going to be 0, which means that what we're going to have is call down is going to be equal to P2 multiplied by 0 plus 1 minus P2 multiplied by 0 present value. So call down is going to be equal to 0. So we have call up and we have call down, which is equal to 0. Now we're ready to find the value of the call today. And the value of the call is going to follow the same pattern, right? In this case, what we need to find is we need to find U here and D here, and then we also need to find P1. So let's apply that. The call value is going to be equal to P1 this time multiplied by call up plus 1 minus P1 multiplied by call down, and then we're going to take the present value of that. Now we know that call up is 2.025. We know that call down is equal to 0. That's what we had earlier here. 2.025 was call up and 0 was call down. That's what we found just now. And the question is, what is P1? So P1 is going to be equal to future value of $1 minus D divided by U minus D. Now, what is U? In this case, is going to be equal to 22 divided by 20. So we're going to do 22 divided by 20. That's going to give us 1.1, which means that D is also going to be equal to 0.9. So our call option price here, if I can get this to work, there we go. Our call option price is going to be equal to P, which is essentially going to be equal to the same thing that we had earlier, right? 0.6522, which is this. And the reason it's the same is because U and D are the same. And here we're still using the future value factor, and T also is the same. So P is going to be exactly equal to that one. So 0. That multiply this time by C call up, which is 2.025, and then we take the present value of that, which is the exponential of minus 12% divided by 4. So what we're going to have is 0.12 divided by 4 equal minus second function present value, multiply that by 2.025, and then we're going to multiply that by the probability, which is 0.6522, and that's going to give us a call option value of 1.281. That's going to be our call option value. So call is going to be 1.28, about 1.281. So we apply essentially the method that we just looked at earlier, which is essentially the assumption that we have, in this case, a risk neutral environment or risk neutral world. This is where we started. We had a risk neutral world, which means that we are earning the risk free on our investment, and so the future price of the stock is going to be the future value of the stock today at the risk free. Using that intuition, we can price the call option, and the call option is going to be the present value of the outcome that we get on call, that are weighted. That outcome that we get on call is going to be weighted by the probability that the stock price increases or decreases. Using that concept, we apply it essentially twice. We apply it in the first time here to find call up, and then we apply it a second time here to use call up to find call here. That's all we're doing there. And once we do that, we essentially have a call option price that's equal to 1.281 about. And that would be the multiple stage valuation using the binomial. Now, we could do this for whatever time period we have, right? So far we had t equal to 3 months, and that's also equal to 1/4 of a year. You could use t equal to 1 day, or you can use t equal to 3 hours. Now, the shorter t is, as t tends towards 0, the more accurate this process becomes, and we move from using the binomial to using what we refer to as the Black-Scholes option pricing model, which we are going to be looking at in the next unit. And that's what the object of the next unit is going to be all about. What I'm going to do next is go back to the slides and kind of recap what we just looked at. So in the earlier video, we looked at this with respect to one stage. That was our risk neutral valuation approach, when we assumed that we are living in a risk neutral world. And what we did essentially is we made the assumption that we're going to earn the risk free on our investment, and if we earn the risk free on our investment, we could price the option fairly accurately. Now, if we do that on a multiple stage, which is essentially what we have here, where we have the first stage that stops here, this is going to be our first stage, and then we're going to have a second stage, and our second stage is essentially going to be this period here. We can apply the risk neutral valuation for this stage only and find the call option value here and the call option value there, and then we apply the risk neutral valuation again in this period here to find the call option price there, using this call option value and this call option value. And so what we're going to have here is call up up, call up down, call down down. And so call up up is going to be the present value of this outcome using probability 2. So call up was P2 multiplied by call up up plus 1 minus P2 multiplied by call up down, and then we took the present value of that. So multiplied by RT. That gives us call up. We apply the same thing for call down. Once we have call up and call down, then we use that all over again to say call is going to be equal to, now we have P1 here, P1 call up that we just found. So this is going to be call up plus 1 minus P1 call down, and then we do present value of that. That gives us a call option price. Now, the more we do that, remember we have to work at every node, so we need to find call up and we need to find call down, and then we need to find call. And that's essentially what we have here. When we do that, we can find call up, we can find call down, and when we apply the valuation again, we get a call option price at around 1.2823. What did we get? We got 1.281, so approximately, I'm sure that's the decimal that is at issue there. But that's essentially what the process is all about. You could do the same thing for a put option. We're not going to work the example of the put option here, but you could do the same thing for a put option and you would have the same answer. We worked on the put option with the single stage. You can apply what they did here for a multi-stage, at least two-stage. For the call, you can apply the same principle to the put option price, and you're essentially going to have the value of your put option price there. All right, and this example assumes that 1 year for this time step, right? So in this case, you're going to have 1 year here, and you're going to have another year. So this is essentially a a 2 years put with the price today of 50, a strike price of 52, first stage 60 to 40, and then 72, 48, and 32. And you can verify your answer that you have put up, put up down, put down down, and then you can find the put down here. You can find put up, and then you can find put 0 or put value there. So to find put up, what you're going to have is, let's call that P prop 2. So you're going to have put up multiplied by probability 2, which is the probability of increasing here, plus 1 minus probability 2 multiplied by put up down, and then present value of that. So you apply the same thing you would have at this interest rate, where U is equal to that, D is equal to that, and P essentially is going to be equal to that. We talked about the delta, and we said that the delta of the option is nothing else but the ratio of the change in the price of the stock option to the change in the price of the underlying. And you remember that we said that delta, which was H, was call up minus call down divided by stock up minus stock down. So that is going to be the change in the value of the option and the change in the value of the stock. The value of delta varies from node to node, and that makes sense because delta here is going to be equal to the change in this value of the option, right, and the change in these prices that we have here, whereas the delta here is going to be equal to the change in this value over the change in these values. So the delta over this period is going to be different from the delta over that period. So it changes from period to period. Now, using this method to hedge a portfolio, you will be essentially using what we call dynamic hedging, where you adjust delta of your portfolio from period to period. You make sure you recompute those deltas as time passes, and you adjust the position accordingly. Remember, delta is essentially the number of shares of stocks that you need to protect the position in call. So for example, if you have a covered call position where you write call and you own a stock, the delta is essentially going to tell you how many shares of stock you need to hold for each call option that you're writing. There, that would be how you use the delta to protect the position. Now we talked about U and D, how it is that we can estimate U. U is essentially like a growth factor of the value of underlying over a period of time, and U, of course, is going to be a function of the volatility of the option, not the volatility of the option, but the volatility of the stock, right? And delta t is just that change in period, right, from today to that time t. So you can use t or delta t. For American option, it's more important to focus on what the delta t is, because the option can be exercised on or before expiration, and so the delta t matters even more for American option than it matters for European option that can only be exercised at expiration. The sigma here is going to be the volatility or the standard deviation of the underlying. Delta t is the length of time step, or you can have multiple time steps. And so if you have multiple time steps, and as the time steps goes towards zero, you start working with the binomial essentially replicates what we have as and what we know of as the Black-Scholes option pricing model. And that's what we're going to be working on in the next unit. Now, the examples that we've been playing with so far assumes that there are no dividends that are paid. So for options on stock indices, currencies, and futures, the basic procedure of constructing the tree is the same, except for the calculation of the probability. And that probability, essentially P, is going to be equal to A minus D divided by U minus D. The way A is essentially going to be equal to what we've played with, the future value of $1 for non-dividend paying stocks. So this, what we've worked with was non-dividend paying stocks, so that's fine. Whenever we have dividends, we need to adjust that to reflect the dividend. And you remember that when we're working with futures, whenever we had income, we subtracted the income yield. So when we had dividend, we subtracted the dividend yield from that return. And so what we're going to do is we're going to subtract the dividend yield again from the risk-free rate of return here when we compute A. That's about all the difference there. When we are working with the currencies, we use the covered interest arbitrage or the interest rate parity theorem. And that interest rate parity theorem simply said that we should make it's depending on how the quotation was or how the quote was. If it was a direct quote, we would take the return of the domestic country minus the return of the foreign country. And that's essentially what we're applying here, where RF is the risk-free rate of return in the foreign country. So the procedure is the same, and we just make sure we account for that exchange rate. And whenever we're working with options on futures contract, we just have A equal to 1. So for futures contract, what we're going to have is P is going to be equal to 1 minus D divided by U minus D. As simple as that. As we increase this time step, so we go from quarterly to monthly to daily, we get a little more accurate. And as we talked about that earlier, and in practice, at least 30 time steps are necessary to give a good option value. So you really want to have, if you're going to use binomial, you want to be using at least 30 time steps, and you can actually create that fairly easily using Excel. It's pretty easy to do. Now in the book, I think it's the first few pages of the book, there's a link to a software that is essentially an Excel software that uses 500 time steps. So it's an Excel template that was constructed by the author, which is John Hall, and I think it's posted on his website, that uses 500 time step for the option valuation. So you could play with that and see what you obtain. And you remember that the more time steps we include, the closer we get to the Black-Scholes and Merton option valuation. And that Black-Scholes and Merton can be derived by looking at what happens if the price of the European call option as the time step stands towards 0. So we are pricing European call option and we are shrinking the time steps. What do we obtain? And what we obtain is essentially that Black-Scholes option pricing model. And that's what we're going to be seeing in the next unit. Alright, so this wraps up our discussion of Unit 11. I will see you in the next video to talk about Unit 12. And Unit 12 is going to be on the valuation of options using the Black-Scholes option pricing model. I will see you in the next video.